cold, but I see the light. Heart is gold, I just need to shine.
That's actually one of the talks. After the talk, we're going to show our first results at 40 minutes. I got your number, so I can good.
everybody, welcome to Physics at Veldhoven, the 2020 edition. As NWO, the main science, we aspire to take the lead in bringing the Dutch scientific communities together to facilitate scientific networking, collaboration and the exchange of scientific ideas and results.
I wish you a warm welcome to the 2020 Physics at Veldhoven meeting. On behalf of the Roundtable of Physics, Advisory Committee to the Board of the NWO Science Domain.
Physics at Veldhoven is the largest conference organized by the Dutch Research Council, where the entire physics community can meet and share their brilliant work.
In the next 2 days, we have the unique opportunity to meet literally all our colleagues in the field and enjoy the wonders of physics.
Because that is where a beautiful science story starts, by hearing something new, by talking to someone new and by seeing new connections.
May this 2020 edition bring you loads of fun and inspiration.
Let's enjoy the beautiful science and don't miss out on the wonderful artwork.
Good morning. Welcome. My name is Alex Ketchaturians from Radboud University, and I've had the pleasure to be the chair of the organizing committee, so on behalf of all of them here today, I'd like to first of all welcome all of you. Now, I think one of the subtle arts of physics is asking short questions and giving concise answers, and I think we should add giving shorter speeches at conferences. So from that standpoint, I will try to say a few words and keep it concise so we can jump into the excellent science. I've had the pleasure over the last year to work with numerous young, vibrant, enthusiastic scientists to organize the program you see here today. I think we're all very excited with what came out. We've had up to 1,700 participants subscribe to come today, and that's included a list of more than 200 speakers ranging from all of the fields, and we feel that it's well represented in the Netherlands. On top of that, we've had lots of fun and seeing all the enthusiastic contributions to things like focus sessions, with things ranging with the word quantum in many of them. But also, I've been quite proud as a committee to be able to create new formats in some of the focus sessions to actually have more interactive sessions and to address also topics like diversity. And so we are very happy to see what we can offer there today as well. We've been additionally, let's say, enthusiastic to host 3 plenary speakers today, coming from different parts of the world. And we're going to hear from topics ranging from living matter, all the way over to what non-equilibrium even means, for example, in condensed matter systems. And for dinner, we're going to have a side of black holes as well. That being said, before I hand over to my colleague here to introduce our speaker, on a personal note, I would like to say that Veldhoven for me always felt like that family reunion you have to go to every year. And I've also come to enjoy it, and I know that these days lots of people have concerns about agendas, financing, you name it. But having worked on this program over the last year, I've also seen how much hard work is necessary to make this conference happen, especially on the side of people at NVO. And for that, I'm deeply grateful for the Physics at Veldhoven team. We're even concerned about some of the nuances, including just having good heating in this very room. And therefore, I would like to personally ask you today, should you run into one of these NVO officers, share your experiences with them about Veldhoven, things that you like, things that you would like to see improved. And from my own experience, I'm pretty sure they'll show you the arts of dancing on the dance floor, which is also available for you tonight. And I know this would be greatly appreciated. So that being said, I would like to thank you all for your participation, and I would like to welcome on stage Shirin Faraji, who's going to introduce to us today our first plenary speaker.
Good morning, everybody. It's my great pleasure to welcome you here, and it's so wonderful to see so many of you here. Thank you for coming. Professor Andrea Leo, we are honored to have you here, and thank you for accepting our invitation and traveling all the way from the US to here to participate and also share in Physics at Veldhoven 2020. Thank you. Andrea is a professor of physics at the University of Pennsylvania. Her research uses both mathematical analysis and computer simulation to study soft matter and living matters. Andrea graduated from University of California, Berkeley in 1984 and earned a PhD in 1989 from Cornell University. After postdoctoral studies at Exxon and University of California, Santa Barbara, she joined the faculty at University of California, Los Angeles in 1994, and she moved to University of Pennsylvania in 2004. Today, she will tell us about how to use machine learning techniques as a new tool to learn new physics learning. So prepare yourself to be challenged, excited, and inspired. And Andrea, the floor is yours.
So thanks very much. I'm not quite sure where I'm supposed to stand. Maybe I'll sort of stand over here so I can look at the screen. Oh, I see. I've got the screen here. Anyway, yeah, so what are we all here for? So let me just start by saying, why do we all take statistical mechanics? Right? Everybody has to take it. And I think it's really nicely summed up by this quote by Helen Keller, that alone we can do so little, together we can do so much. And that's the precise idea, right? If you just have individual atoms, okay, they're very interesting to study in themselves, but you put them together, you put in interactions, and you get new phenomena when you put many of them together, collective phenomena that are really surprising. So, for example, you can take copper atoms, right? They can conduct. Okay, if you put many of them together, you can get a conductor at higher temperatures, but at lower temperatures, you can get a superconductor, right? If you take liquid crystal molecules, we can understand a lot about individual liquid crystal molecules. You put them together, you can get ordered phases, you can get defects in those phases, and that's what gives us liquid crystal displays. If you look at water, right, just put a bunch of water together, we know you get this usual gas, liquid, solid phase diagram with a critical point where the liquid and the vapor become identical. And there are all sorts of fascinating phenomena and universalities that appear where there are quantitative connections across very different systems, from anisotropic magnets to binary alloys to liquid vapor systems, right, that they all are described by the same numbers. And understanding that, right, was one of the triumphs of modern physics. All right, so that's what statistical mechanics is for, really. It's for reaching this central goal of condensed matter physics, which is to go from microscopic information, okay? For example, if I'm talking about a classical system, right, maybe the phase space variables, the positions and the momenta of all the particles, to go from that and the interactions between them to understand collective phenomena like phase transitions and other things in many body systems. And when you think about this, this is a too much information problem, right? You start out with all this information, all the positions and velocities of the particles, for example, and you reduce it down to distributions of microscopic quantities, okay? And eventually, we typically look at averages and variances of those distributions, and statistical mechanics helps us to connect those to the collective phenomena that we're interested in. So it both solves this too much information problem, which is a dimensional reduction problem. You're going from, the many dimensions of phase space, all the positions and velocities, possible positions of velocities, down to just a few variables that are going to tell you about the phenomena that you're interested in. And at the same time, it provides this bridge from the microscopic information to the macroscopic collective phenomena. So that's been tremendously successful for over a century. We understand so many problems in condensed matter physics from that. But sometimes it doesn't work, okay? And the big one, right, is when you're far from equilibrium. So statistical mechanics is, you know, it's for equilibrium systems that are in equilibrium or near equilibrium. When you're far from equilibrium, it's not as powerful. We don't really have the same level of tools. And so an example of that, oh, that's one thing. The other thing is what happens if you lack symmetries. For example, if you lack crystal symmetry, okay, if you have a disordered system, things become harder. You can still do a lot in statistical mechanics with disordered system, but again, our tools are not as powerful. And finally, what happens if you have a nonlinear response? So if you push on something hard enough, okay, so the linear response, where again, we have really nice tools and statistical mechanics breaks down, then again, we could be in trouble. And problems that sort of exemplify all of these three problems all at once, okay, are problems in which disordered systems go from being fluid to being rigid. So for example, if you have the glass transition, the top, you start out with individual atoms, right? Put them together with interactions. You can get a molten glass, which is like a liquid, or it can be solid when it goes through the glass transition. Or you put a bunch of grains together, right? You can pour sand like a liquid, or you can walk on the beach, you don't sink through it. It supports your weight, it acts like a solid. Okay, and this is the topic of yesterday's master class. So what I'm going to do today, since I talked about it yesterday, I know only to a tiny fraction of all of you, but I'm going to sort of distill that part of the talk into 5 slides and then go on to even additional challenges beyond these, okay? So, let me first talk about. So basically what we have done is we have used big data analyses to both solve the too much information problem, dimensional reduction problem, and to make that bridge from the microscopic to the macroscopic scales, okay? And we've done that on 2 different problems. So the first problem is that of glassy dynamics. I'm going to summarize that quickly for you, and then I'm going to spend more time on the second problem, which was inspired by biological function. Okay, so the first problem is the glass transition. So the glass transition is completely generic. If you take any liquid and you cool it down quickly enough so that it doesn't have time to crystallize, then you will get a glass transition. And when you do that, the particles remain in a disordered configuration the whole time, so there is no crystal symmetry, right? What happens as you cool it down is that the time to reach equilibrium, or if you apply a stress, the time for that stress to relax, or very similarly, the viscosity of the system, goes up continuously. And it can increase by 10 orders of magnitude in just tens of degrees. It's an incredibly rapid rise of that relaxation time. And because that's a time to reach equilibrium, as you cool down, very rapidly you get to a point where you cannot equilibrate on any reasonable time scale that you're willing to wait. And at that point, you just say you have a glass. It's now solid on your reasonable time scale. So what's happening? So if you apply a stress, the way that stress relaxes is from particles moving around each other, right? That's the difference between a liquid, where particles can move around each other, and a solid, where they maintain their neighbors. And so in a liquid, any particle can rearrange at any time. In a crystal, we know that particles that are at defects, like dislocations, are far more likely to rearrange than the ones that are in crystalline regions, in crystalline environments. And so the challenge has been for glasses and glassy liquids, are they just like liquids where any particle can rearrange, or are there certain particles that are much more likely to rearrange than others? And how do you find that when the system is disordered so everything is a defect? And that's been a 50-year-old plus challenge. People have been banging their heads against this problem for a long time. And the problem is that if you look at the structure, if you look at snapshots of the system, and I told you this is a liquid and this is a glass, you would not really be able to tell the difference. Okay, you cannot say, aha, now I've gone through the glass transition. There's no structural signature of it. And it turns out that this is exactly what machine learning is good for. Because machine learning is designed to find very, very subtle correlations. And this is something that, you know, people have been looking for and not being able to do, and it turns out to be incredibly easy with machine learning. Even the simplest methods work. So I'm not going to tell you exactly how we do it. I'm just going to summarize the basic idea. Instead of looking just at one quantity, you look at many. Okay? And this could be, for example, what is the probability of finding a particle at some distance r away from your particle of interest? Okay? So that's what's called the radial correlation function, or the pair correlation, G of r, in statistical mechanics. So, you know, here's the plot on the right. That plot shows G of r. It's very unlikely to find particles that are too close because they repel each other at short range. And then they build up. There's a peak, that's the first shell of neighbors. Okay, and then there's a valley, and then there's a second shell, a second peak, and so forth. So that's what it looks like for a liquid. And this is a numerical thing, so that it's a discrete weighted sum, but in the continuum limit, you can think of this machine-learned quantity as just an integral over the pair correlation function for each individual particle I. So I just look at the local structural environment of each particle I get the local pair correlation function, and I have some weighting of it. Okay, some weighting function, W of r, which is the same for all of the particles. Okay, and that gives me this quantity that I'm going to call the softness, okay, which is designed, the weights are chosen by the machine learning to make softness correspond. It's a structural quantity, but it correlates very, very strongly with the rearrangements. Okay, and it works. Okay, so this is a movie. This is a movie of a Leonard-Jones mixture that's close to the glass transition, above it. Okay, and now I've colored it by whether they have positive softness or negative softness. Positive softness is likely to rearrange, negative softness is not. That's blue. Okay, so positive softness is red, and now I'm showing only the particles that at that moment are rearranging. And what you see is that 90% of them are soft. Okay, so this quantity actually does work to predict rearrangements. So that was nice. You know, that was a thing that people have been trying to do that was very hard, and machine learning, it turns out it was easy. But in terms of our program of understanding collective phenomena, so what, right? So you can do it. What do you do with it now? So the idea is, right, if I have the softness of each particle, that's still a microscopic quantity. So it's only useful for me to do, you know, statistical, or to do condensed matter physics if it tells me something about a collective property. And in particular, I want the average softness, which is the average over all the particles, which is now just the same weighted integral, but of the average pair correlation function. Okay, I need to connect that to some property that I'm interested in. And it turns out that we can. So this is a plot of the relaxation time versus the average softness. This is for two systems. One, the Leonard-Jones system. The other system is just like the Leonard-Jones system, except it only has the repulsions. These two systems have very similar pair correlation functions. They're so similar that I can use the same weighting function for my softness for both of them. Okay? And what you see is that the relation, even they have very different softnesses and they have very different dynamics. The relaxation time is a function of temperature. It looks totally different for these two. Okay? But if you plot relaxation time versus average softness, you get the same relation for both of them. And I didn't show that, but we actually have a curve, okay, that goes right through those points. Okay? That's what's called a fragile glass. There's another example, which is a network glass. This is like window glass. Okay, where instead of relaxation time, I've plotted something very similar to the inverse relaxation time. That's the diffusion constant. Okay, so people look at, for example, the diffusion constant of oxygen atoms. And the points are from simulations, this diffusion constant. Okay, the line through that comes from our softness analysis. And you can see that we can understand the behavior at that relaxation time, which is a collective property as a function of temperature from the average softness. So that is what we wanted to do. We wanted to describe a collective property, in this case the temperature dependence of the relaxation time, in terms of an average over some microscopic quantity, which is softness, okay, and we can do that. So that works, okay? So just to sum this up, right, machine learning, what it's for is to identify subtle correlations that are hard to pick out. And there are many, many problems in physics where we're trying to find subtle correlations, and I think machine learning is a very powerful tool for us. And the other thing is that, you know, because of this fact that we can describe actually not only the relaxation time, but many other aspects of the classic dynamics, machine learned softness, we think, is a very promising basis for a theory of the glass transition. Okay, so I talked about these systems, which are far from equilibrium and disordered, okay, and it can have nonlinear response. Now, we go to biological systems, and they're even worse, okay? They're even harder from a statistical mechanics point of view, because even though we can understand disordered systems to some extent, biological systems are not ordered, and they are not disordered either. They are designed to have functions. So for example, if you take a protein, okay, it has some amino acids, a sequence of amino acids. Those are not chosen randomly. That's not disordered, okay? It is designed in order to be able to fold, and then in order to be able to perform some function, okay? And that's something that we really have no handle on, how to handle systems, many-body system. A single protein is already a many-body system. How do we handle this of interacting, you know, atoms that make up the amino acids, okay? How do we handle this when they are designed, okay? So we're going to focus on a specific example, which is allostery. So this is something, for example, that enzymes have. So man-made catalysts can't be turned on or off. They're either on or they get fouled and they turn off, okay? But enzymes can be turned on and off. And most of them do it by this mechanism of allostery. So the idea is, suppose you have this red triangle as the substrate molecule. That's the molecule that wants to bind to the enzyme and get chemically modified and go off, okay? This is a case where it cannot bind. Okay? Naturally, it cannot bind to the protein until some other molecule called a regulatory molecule, which is the green circle, okay, binds to the protein. Once that thing is bound, okay, it causes a conformational change of the protein, often far away, okay, and that allows the substrate molecule to bind and get chemically modified. So this is the case of turning the enzyme on. And if I think about this from a physical point of view, what's happening is that the regulatory molecule, by binding, is changing the conformation, so it's exerting a strain at what I'm going to call the source, okay? And the result is this protein is designed so that the strain at the target, where the substrate binds, is a prescribed amount, and that allows then the target, the substrate molecule to bind, okay? And you think, okay, you know, so it's on the other side of the protein, big deal, elasticity is long range, okay? But in fact, you get a localized strain that is comparable to the source strain that's far away is not something that would happen naturally in elasticity. For proteins, you know, it would normally decay to about 10 to the minus 2 of the source strain at that distance away. So to get a response that's of order 1 compared to the source strain is unusual. That requires work, okay? Or that requires thinking. And proteins thought about it and evolved, whatever they evolved in order to achieve that function. So the question is, how do they do it, okay? That's the question that we want to address. Now there's a second example, okay, which is the brain vascular system. So it's very interesting. The brain uses most of the oxygen, 25% of the oxygen that comes into us, okay? And it directs that oxygen to the places of the brain that are doing the most work at that time. So if I'm talking, right, the brain is directing extra oxygen to the speech centers of my, okay, in my brain. I'm thinking, hopefully I'm thinking as I'm talking to you, and therefore blood flow is actually going to those parts of the brain as well, okay? But then if I stop thinking, okay, and I start walking, all right, that's a different part of my brain that needs more oxygen. And the way the brain does this is that it contracts individual vessels and dilates others in order to direct extra blood flow to certain targeted regions, okay? Now, the source is the arteries. That's where the flow is coming in. There's a large pressure drop across the arteries. And now the brain is adjusting the conductances of different edges of the brain vascular network, different, connections in the brain vascular network channels, in order to direct the target flow. And you can see this is just like allostery, right? I put in something at the source and I'm directing it to the target. And the brain is doing this in real time. So how does it do that? I can call that flow allostery. How does the brain achieve that function? Turns out that mechanical and flow systems are actually very similar. And you can think of it as in flow networks, which are just like electrical resistor networks, really, right? You have Kirchhoff's law that there's no net flow at every node of your network, okay? In mechanical networks, you have to have force balance on every node. There's no net force on every node of your network. And that similarity causes the mathematics to be very similar, so that flow networks are essentially a 1D version of mechanical networks. All right, so I'm going to start out now by saying we're going to apply big data methods, but I'm going to say something very profound, that big data requires lots of data, okay? And so usually, what people do is they look across protein families. Let me look at the same protein across many different species where the protein has the same function, but they're slightly different from species to species, and that gives me then a collection of proteins that I can look at. That, from a statistical mechanics point of view, may not be enough, okay? We want to have all the representative things that can give that, right? You need to have many microstates in order to get a good average. And so we don't really have enough data, okay, from the biological literature. So how do we do this? Our approach is actually to design mechanical networks that have allostery. And then, instead of starting with a real folded protein and turn it into a spring network, there's a healthy community of people who do that, okay, and then studying that mechanical network, which is just nodes connected by springs, okay, we're going to make our own networks that are designed to have allostery. So then we can create as many of these as we want. We can create thousands of networks that have the same function, okay, and do an ensemble average. So how do we do that? I'm not going to say too much about it, but the idea is to introduce what I call edge daemons, like Maxwell daemons, that can go in there and modify the properties of individual edges or bonds in this network. Okay, so in the mechanical networks, they tune the stiffness of the springs. In a flow network, they tune the conductances of the edges. Okay? And the idea is to approach this as a computer scientist would approach it, just say, okay, I want to impose constraints on the system. I want the target strain to be at least as big as some desired amount, okay? And then I adjust the degrees of freedom, which are the bond stiffnesses, in order to minimize the cost function that enforces that. Okay, so if I reach the global minimum, then I have a target response that's at least as big as what I wanted. Okay, and then we use greedy edge daemons that minimize the cost function most rapidly, okay, to reach that global minimum. And it works, okay? Uh-oh, I did not animate that last thing. But here is that is a pity. So here we are tuning the target strain, so the strain at the target is in the upper right on this movie on the left. The blue dashed ones are the ones that are totally removed in this process, okay? And at the end, we've achieved the target strain that we want, okay? On the right, I have a flow network, so the target pressure drop is on the right. And again, I'm tuning conductances as this movie goes on. The blue dashed ones are the edges that are completely removed in this process. And eventually, I reach the pressure drop that I want, which is 0.2. Okay, so we can do this, all right? And it turns out it's very easy that we can do this with over 99% success, removing very few bonds. So in a protein size object, you need to remove, in the end, about 5 bonds to get allostery, to get a response of order 1 at the target that's the same, a response at target that's the same as the source. Okay, so now, oh yes, and we can do this. We can take small ones and we can laser cut them, and it works. Okay, so this isn't a small example. So look at the target was where my fingers were initially. Now I'm pulling at the source, and you see the response at the target. Okay, and we can 3D print them as well, so you can three-dimensional versions. Okay, all right. So now we've done it. We've got ensembles of networks that all had the same function. Okay, they're different networks that had the same function. So I've got a lot of data now. And what do we want to understand? We want to understand what are we doing to the network that enables to have that function. How do these microscopic edge demons, these changes in the edge conductances, add up to give you function, allosteric function? So I'm going to start out with float networks, where we can think about it in a very simple way. Okay, so the idea is, suppose I have a flow network where I have some source pressure drop across those 2 red nodes. Okay, so the pressure difference between those 2 red nodes is, I'm just going to call it 1. Okay, and I want to have a pressure drop across the 2 green nodes to be 1 also. I want all of that pressure drop to be communicated to the target. What ends up happening is that the system divides essentially into 2 pieces, so that the blue ones on the bottom plot on the left are the ones that are removed, okay? And what you end up with is all the nodes on the inside have a pressure of -1/2, and all the ones on the outside with the plus signs have a pressure of +1/2, so that the pressure drop between the 2 sections, inside and out, is 1. Okay, the pressure drop across each of the removed bonds is 1. Okay, the second example is, this is with periodic boundary conditions. So these 2 are the same. Again, the system is breaking up into 2 pieces with different pressures in the 2 sectors. Okay, and this is a topological change. It's the topology here that has changed, right? There now, what was 1 network is now 2. Anytime you can count something, that's topology. Okay, and the idea is that the 2 target nodes span those 2 sectors. Okay, so, and I could have removed the bonds along any line. As long as I decompose it into 2 sectors, I would get the target pressure that I wanted. So there's nothing unique about those particular bonds that were removed. I could have chosen any sort of curve to enclose the inner sector. Okay, so since this is a topological change, now we want to ask, well, what if we're not doing this extreme example? What if we only want a target response that's 0.2 of the source? Okay, then what? And the idea is that persistent homology was developed by topologists as a method of finding topological features that are obscured by noise. Okay, in this case, it's not noise. In other words, if I do not have a target pressure drop that's 1, if it's smaller than 1, the network is still all 1 piece. There is no topological change. It doesn't break up into 2, except in that extreme case. But I can find the remnants of that behavior, maybe, okay, using persistent homology. That's what we thought, and that's why we tried it. And it does work. That's why I'm telling you about it. Here is that network that I showed you before. The top right plot is that extreme case where it's tuned, okay? And what you see is if I look at the average node pressure in the orange sector and the average node pressure in the right the green sector, the difference between those averages is 1, which is exactly what I tuned in. Okay? Now let me go to the next one, the third one from the left, or the second from the right. Okay? There I tuned in a pressure drop. I asked for it to be at least 0.2. It turns out that I got about 0.29. Okay? And if I look at the average pressure in the orange sector and in the green sector, it is what I tuned in again. And I can even do that when the target pressure drop is 0.05 of the pressure of the source. We can even still identify sectors and look at the difference in the average and get very close to what we tuned in. Okay? We can tune in multiple targets. So here's a single source. The bottom set is there's a single source pair in red, and there's 6 different target pairs if you look closely. And here the system for persistent homology gives us multiple sectors, okay? And if you look at the pressure drop across any 2 sectors, a target that spans any 2 sectors, you get the right thing, okay? So the persistent homology analysis really does work. And this is just show quantitatively for thousands of these that the sector pressure difference in the average pressures of the nodes in a sector is what you tuned in, okay? So, just to say, in the case, and when you do persistent homology, what you do is you add in edges. You start out with a blank network, and then you add in the edges of the network in some order. And we do it in the order of increasing pressure drop across a given edge. And that's called an ascending filtration. You can also do it in an order of decreasing pressure drop. So you start at the highest, and then you add them in order from highest to lowest. Okay? And in the case of and this ascending filtration basically gives you these sectors, okay, where you see like the green and the orange sectors. Whereas the descending gives you the removed edges. It gives you those cracks, okay? And the cracks and the sectors are really the same thing because the cracks just are at the edges of the sector, at the boundaries of sectors. If you look at mechanical networks, because it's a vector problem, not a scalar problem anymore, they're more complicated, and the ascending and descending filtration give different things. And it turns out that there are 2 numbers that are important, which one is from the ascending filtration, which gives you the sectors and hinges or boundaries of sectors. So we call that that number the hinge persistence. And the other thing is from the descending filtration that gave you the cracks in the flow case, and that gives you, in this case, pathways of strain, where a strain at the target, at the source, is just communicated through a path, pushing this, that pushes that pushes the other thing, and gives you a pathway through this thing that communicates the strain. And that we call the pathway persistence. Now, the confusing thing about allosteric proteins is that there are many, many mechanisms that have been proposed. People say, oh, this protein has a hinge, it does something like this. Or this protein has a shear band, it does something like this, okay? Or this one is like scissors, it does something like that, okay? Or this one has a strain pathway, so it just pushes right through, okay? And the point is that you can get all of these behaviors. There's actually a continuum behaviors. So depending on these 2 numbers, the strain pathway persistence and the hinge persistence, okay, this is a heat map for all of our networks of how many are characterized by a given pair of these 2 numbers. So blue, there are not very many. Yellow, there are a lot of them, okay? And these orange symbols correspond to these different realizations. So depending on where you are in that sort of diagram, okay, phase diagram, you get different behaviors, okay? But there's really a continuum. What this shows is that there's a continuum. There isn't any specific mechanism. There aren't discrete mechanisms, okay? And that's a new insight, okay? And we think that this is why the mechanism of allostery has resisted easy classification. This actually works. So if you look at the hinges, if you look at the sectors, you can predict the strain much as we could predict the pressure drop and the average pressures of the nodes. You can predict the strain due to allostery, and as long as your hinge scale is big enough, you can get quite good overlap, about 75% with the actual motion, okay? And now we can ask, what about proteins, okay? So we can take real proteins, we look at the crystal structures and look at what happens with and without the regulatory molecule bound. There are quite a few of those. And we can analyze those and calculate these two numbers and put them on that scale. And what you see is that, you know, they fall all over, right? As you would expect. And again, if you characterize those, take those numbers, look at our analysis and say, how well does it capture the actual strain that is predicted? It's around 75%, as long as the hinge scale is big enough. So it actually does work for real proteins. And this is an example. This is glucokinase. Okay, it's actually a variant of glucokinase. It's a drug. Okay, the source is at the inner side of the hinge, and the target, no, yeah, I think that's right. The target's at the outer side of this protein, so the source is green, the target is purple, okay? And here's a picture of the protein. Okay, what we're showing is the sectors. So the blue is one sector, the red is another sector, and the strain pathway is this black line in here. This is a case which is very hingy, okay, has had very large hinge persistence. And if I look at, on the right, I have a picture of the proteins that are conserved. In other words, if I look across families, these are the amino acids that are repeated over and over again, that consistently appear. And the ones that are most highly conserved, that are most consistently appearing across species, are the ones in white, okay? The ones in blue, it's a scale from white to blue, so blue is not very conserved. And the ones that are most highly conserved are the ones actually at the boundaries of the sector. Okay? So it does maybe seem to tell us something. All right. So this has implications for experiments. So in flow networks, the brain vasculature, what people have been trying to do is map out that vascular system perfectly, right? It's very hard to map it all out and to characterize it. And it's like in the brain, right? Mapping all the connections between neurons, it's like calculating the connectome for the brain vascular network, or measuring the connectome. Okay, but that requires, in order to make progress that way, you really have to completely specify all of the edges. And our results actually say it'd be more useful to measure the node pressures, and then incomplete data could actually be used to still identify the sectors. All right. So let me just sum up. So we've reduced, this was dimensional reduction, right? In the end, we had reduced the function of allostery to two variables, hinge persistence and pathway persistence. And we find that that is actually useful for understanding the function. Allostery is something, generalized allostery, that appears in lots of different networks. For example, ecological networks. When wolves were introduced into Yellowstone National Park, the beaver population went up. Okay? That is, again, some source, increasing number of wolves, some target, the beavers went up. Okay, of course, the intention was not to make the beavers go up, but that's what happened, right? So biochemical signaling is the same thing, okay? There's some protein that receives some signal. There's a cascade of proteins that then get activated, and then, you know, suddenly you drink some caffeine, and then suddenly you're awake enough to listen to this talk. You know, again, that's a form of allostery. And of course, there are memories in neural networks. You train a neural network, it learns something, right? Again, there's a source, you gave it all these images, and there's a target. It said, this is a cat, okay? And maybe these memories actually have topological signatures, and we can use a variant of this, a generalization of this persistent homology approach to figure out what that is, or for any of these systems, okay? Our approach, which was first to use unrealistic mechanical networks just so that we could design them to have this function, to get statistics, to get ensembles, and then to use data mining methods, in this case persistent homology, okay, to identify the mechanism, and then take that analysis and apply it to real systems, was useful here. I showed you the machine learning, where we could do something there, but how generalizable is this? So I just want to say that, yes, I think big data it's just designed for dimensional reduction, so it makes sense to use it towards the central goal of condensed matter physics, okay? But for each problem, we may need a different kind of analysis, and that's where, you know, our ability as physicists comes into play, right? To think about it and to figure out what is the right way to do it and how to take that analysis and then turn it into physics. So I think there's a lot of room for this across many different problems, and I hope more people start to do it. So just the people who did the work on machine learning, on design and the persistent homology analysis, and and that's it. Thanks very much.
Thank you very much for this very fascinating and stimulating talk. And I'm sure there are lots of questions, and people will use the opportunity to approach you during the coffee and the lunch break. And it's a tradition, and on behalf of everybody here, I would like to give you this gift as a symbol to remember this event and us.
Thank you very much.
And please join me to thank Andrea again. Thank you very much.
Thank you. All right.
Dear guests, the focus session will start at 11:10, but first a few general remarks. NWO information stand is located in Kempensal in case you have suggestions and questions for NWO. In Kempensal, there are also stands for NNV and Lawrence Center. Next, in Kempensal this year, we have, instead of having a regular experiments, we have art experiences. And in case you would like to test your own creativity, so welcome to stop by. And indeed, today we have a walk-in workshop on soft robotics arts that starts from lunch until 6 p.m. So please use this opportunity to test your creativity. New this year is also an exhibition platform located in Mayer Foyer, I hope that I pronounced it correctly, right outside the Kempensal with an interesting palette of companies and institutes. So feel free to also visit there. Last but not least, today we have an NWO information session on KIC 2020-2023, instrument and knowledge utilization during lunch in Brabantsal, starting at 1:20 p.m. With that, I would like to wish everybody an amazing conference time.